center for this kind of activities. So I will be talking about Boussinesq equation. And the point of view is that we have so many, usually we have so many discrete versions of a continuous equation. So I will show that this actually is also true for the Boussinesq equation. So let me remind you first what was the equation that Boussinesq himself wrote in his paper. Is this equation here. This exact form. But of course we can have various other integrated forms, once or twice integrated, and also the bilinear. It's not working. Okay, now it's good. Very good. So this is the equation, but there are also other kinds of Boussinesq equations you maybe know. Modified Boussinesq equation has some extra terms here, and the Schwarzian one. Then there's a classical equation called classical Boussinesq equation, like this. Now, what is a characteristic property in all these is that fourth order in x here and second order in time, which I sometimes call y, and also here. So this is a problem in sense of discretizing, because if we have a second order equation, then we need more complicated initial value than with the KdV equation, which is first order. So there are two ways of doing it. The typical KdV evolution in discrete space is like this. You need one initial value, and then you can, using it, you can calculate the next step in the evolution. But now, if you have a second order equation, then you need two sets of initial values, and then using these you can calculate the next level. Or you can still stay in this framework, but then you need several components. One is the field, and one is its derivative, so you carry them along. So the discretization is a little bit more complicated. Now I will approach this problem from 2 points of view. One is the top-down approach. Namely, we know that the continuous case, we have this higher level KP equation, and by reduction we get the KdV, and another reduction we get Boussinesq. Okay, now in this higher level we do the discretization, and then we do the projection at this from this higher discrete level. This is one approach. The other one is the multi-component consistency around the cube approach. Then we stay in the quadrilateral approach, but we have several components, and this is then another approach to it. And we get we do get equations from both sides. So from this higher level approach, we start with KP equation. I will first show how it works. The reduction idea works in a continuous case. Then we try to imitate it in a discrete case. So this is the KP equation. And then this equation has this kind of solutions. So this is a characteristic property of the KP equation. We have these solutions. This is the plane wave factor, and this is a two-soliton form, but it can be extended to n solitons. And this is a phase factor, and this is a plane wave factor. These characterize the solution. Then the KdV equation is a two-reduction. So what does it mean? As you can see, KdV equation should not have this variable here. It only has time, x and time. So I have to eliminate that, and the 2 reduction means just this, that I choose the q variable before to be minus p, then this drops out, and this phase factor becomes the normal KdV phase factor, and then you can verify that this is the equation. There's no y anymore. So this is the reduction process for KdV. Now Boussinesq, we do the 3 reduction. So we have to put this term 0 somehow. So we use some cubic root of unity here. So if you do this substitution, there's some extra scalings you don't have to worry about. Then the phase factor becomes this. So this is typical for the Boussinesq equation. If I see some solution with this kind of phase factor, then I will guess that it is the Boussinesq type equation. And the plane wave factor is this. This is a continuous form of the plane wave factor, but this phase factor should be the same in a discrete version. Okay, so this is what happens in a continuous case. There's also so-called pseudo-reductions, meaning that you can add some extra coefficient here. And we can also could study the modified Kp equation, and there do in this frame for this equation we could do the 3 reduction or 3 pseudo reduction, and there's still another reduction which gives the Kaup's Boussinesq equation. So okay, let's now then see. First we have to do the discrete Kp equation, the highest level but discrete. Then this will be the bilinear form, and now the one question is, what is the definition of when is a discrete equation in Hirota bilinear form? Bilinear forms are characterized by gauge invariance. This is a very important property, but easy to verify that if you make this kind of linear phase factor, then it can be pulled out. So this, by the way, in this, this is enough to characterize Hirota's bilinear derivative, this requirement. Now in a discrete case, when we have discrete variables, it just have some powers like this, and then the discrete Hirota bilinear form can then be obtained that it's a sum of terms, and in each of these terms the sum of these shifts is independent of the terms. So it is composed of terms, bilinear quadratic terms, which have the same shift in all of the components. For example, here, this is the Hirota's equation, which was written by Miwa in this form. You can see that the total shift in n is 1, and in m is 1, and in k is 1, in every term. So this is in Hirota bilinear form. Okay, so this I can consider to be the top level equation. Now I'm going to do the reduction to get the KdV and Boussinesq equations, discrete forms. So here's also the soliton solutions, the parameters, the phase factor and the plane wave factor. Okay. And you notice that it's totally symmetric. N, M, K, there's no difference. Whereas in X, Y, Z, T, there was a big difference. Okay, so what is a 2 reduction? It means that I take again P, Q is minus P, then this plane wave factor becomes this, but the phase factor becomes, this is already the KdV form of the phase factor. But now there's a problem that we also must reduce the dimension, because the equation was 3-dimensional and KdV is 2-dimensional. So I have to somehow reduce the dimension. So the dimension reduction means that I must be able to choose some shifts mu, and kappa, so that this term is 1. it means that if I make this shift, nothing happens. So in the KdV case, we can take k is 0, mu is 1, and mu is 1. And then to cancel this to be 1, I take b is minus a. So the net result is here. This is then the equation, discrete bilinear KdV equation. And indeed, if you take the double continuous limit, you get the KdV equation. So this method seems to work. So let's do now the tree reduction, same way. So start with this requirement that this is 0, and q is then omega times p, where omega is the cubic root of unity. If I make the substitution in the formulas that we had before for Hirata's equation, then in Miwa's form, then you do get the phase factor in the Boussinesq form. So we are on the right track. But this is still three-dimensional, so I have to make the dimensional reduction somehow. And it's given here. This is the dimensional reduction. Shifting n, m, and k altogether should add up to no effect. So here are the terms. And how can this be 1? Well, if you choose b is omega a and c is omega squared a, then this becomes 1. You can easily see. So now the net result is here. This was the reduction. Then I can use this reduction formula to eliminate k, and I get this equation. And this was already given in the other Jarmo and Miwa. So this I call a bilinear form of discrete Boussinesq equation. And indeed, if you calculate the continuous limit using this kind of function, then you get the bilinear Boussinesq equation. So let me elaborate a little bit about the continuous limit. So if I make a shift of one step or new steps in n and new steps in m, then I pick up some small parameter. I must have some small parameter and have this term here times epsilon, and here I have epsilon squared. Now if I substitute this tau into this equation and make this calculate the epsilon limit, then I do get this one at the epsilon 4th order. Okay, but there are other higher level equations. This is the BKB equation. So it's slightly different in that this term was missing in the Hirata's equation, but it's in this 4-term equation. So it was given by Miwa in 1982, and he also gave what are the plane wave factors and what are the phase factors. So now again, I want to do the reduction and try to get the Boussinesq equation out of this. Well, actually, I can't do the full reduction because probably it's too general, so I will specify one particular case with a particular parameterization, and I do the same reduction. But now notice that if this looks like the cubic root of unity type of condition, if this is 0, then O1 must be cubic root of unity times O3. So, but I don't do that yet. I just keep two parameters here. And then what happens after that is that I can write the previous equation after some change of variables. So I have here k prime, and previously I have some p's and q's. I don't give you the transformation. It's a little bit complicated. But anyway, I can write it something that looks reasonable. And what's most important is that I get something that looks very much like a Boussinesq equation, phase factor, except that I have this extra term, and if O1 is omega times O3, then this drops out. So this would be good enough for me as a discrete Boussinesq equation. And indeed, if I calculate again the double continuous limits with these kind of shifts here, and remember that O1 and O2 go to 0, O3 go to 0, but they scale out here. So I do get the Boussinesq equation. So now I already have two discrete versions for the Boussinesq equation, bilinear discrete version. But there's more. So now I go to the other approach, where the starting point is quadrilateral equation with several components. So here the integrability, definition of integrability is consistency around the cube. So what does that mean? It means that our equation lives on this square, on this plane. We pick up one square, and we have an equation that connects the values at these corner points, and it is multilinear. Okay, so we have some equation here. Now we extend that into 3 dimensions. So we still have this equation, but we have now extra coordinate, which is 0 here, but here it's a shifted. So we have built a cube. Now we put equation on all sides of the cube. So at the bottom we have this Q1, 2, and then on the sides we have some other equations that contain the various shifts. And I jog your mind with using different notations all the time. But this is what you must learn if you want to read this literature, because everybody uses different notation. I'm sorry. Okay, so what is the problem here? If we are given values at this point, this point, this point, and this point, then using this equation, I can calculate this. Using this equation, I can calculate this. And in the back, I can calculate that. But now I have 3 ways to calculate the red value. This way, and this way. And the requirement that this value is the same is the integrability condition. And it's a very strong condition, in fact. So we can accept this as a definition of integrability already because it's very strong. Okay. So here are some examples of equations that satisfy it. But then we also have a classification using this principle of consistency around the cube by Adler, Bobenka, and Zurich. They also assume symmetry and tetrahedron property, but at least the symmetry property has been relaxed. So, but anyway, this approach resulted in a very nice classification and lots of, not too many equations to work on. So, but now we go to the multi-component form because we need several components for Boussinesq equation. So this particular equation was proposed by Tongas and Nijhoff 2005, but in fact in this work by the Dutch school, Nijhoff, Papa Giorgio, Capel, and Quispel, there were several equations already. But now this equation, it satisfies the consistency around the cube form. Now you notice that this only contains tilde and no shift. So this leaves on one of the sides of the square. And on all the other sides, you also put an equation. And then there is one equation that lives on the square itself. So this is a format of this type of equations. So there are several equations were known. So I looked at the classification problem by just assuming these kind of quasi-linear equations on the sides and then whatever on the remaining square. And the classification result was that really the truly 3-component equations were base equations were known before, but I found out that they could have some extra terms. So these were found in this search paper. So, but still, why should these be Boussinesq equations? So now we have to look at that. So in order to do this kind of comparison, I must write the equation in one component form, but in a bigger stencil, the 3 by 3 stencil I draw before. Then I can take the continuum limit better, because Boussinesq equation is usually one component equation. So I want something one component and then take the continuum limit, hope to get the Boussinesq equation. Okay. So here's one of the equations. Now, if you eliminate y and z, you can do that, and you get this equation for x. So it's a little bit more complicated, but it's not very bad. You can also, in this case, write the equation only in terms of z, or only in terms of y, which is a product of the old y and z. And you get this equation. So this is another equation in this set. So after you eliminate y and z, you get one equation for x. So let's see now what is the continuum limit of this. And I take the continuum limit in both of the variables at the same time. But notice what I have to do. First, I have to take some prefactor, some additive part out. And then here's my new function, x. And notice that I have 1 over p and 1 over q. So p and q go to infinity, and 1 over p and 1 over q are the lattice parameters. And here I have y, and I divide it by p times q. So this is second order. Okay, now I take the continuum limit like this, keeping these things fixed, and I get this. And this is really the Boussinesq equation. And notice that this extra factor b0, it gives the xx derivative, because b0 goes to 0 and p and q go to infinity. So this is a finite number. Okay, so I can also say that this is a good candidate for a discrete Boussinesq equation. At least the continuum limit works out very well. But I had several other equations, so let's look at them as well. So here, this C3, I call C3 equation, has this kind of extra term. And C4 has slightly different extra term, but it is also, both of these are consistent around the cube. Now, if you eliminate z and y, it's not so easy if you just giving these to figure it out, but you can do it, and this is the result. And the red part is again the new part. This was known already to Frank, for example, but these are the new terms. Depends on which one I have, so I have different possibilities here. Okay, now the double continuum limit is now taken this way. Here, I elaborate it here. And if you do this limit, then you get the Schwarzian Boussinesq equation with this extra term. Remember, either this or that was possible in the discrete case, but somehow they combine in the continuous limit. And here is the, okay, so this was in terms of x, and now C3 I can also do in terms of z alone. So this was a C3 equation. Now I make eliminate x and y and express my result in terms of 1 over z, then I get this. This is the same as this A2 equation, but notice where my parameters now sit. Now normally maybe you said I can absorb this term into here. But in the continuous limit, they behave differently, so I want to keep them separate. So now I go, so here is it again, and now I take my double continuous limit as follows. All these go to infinity, but they go with same speed. So this here goes much faster than this term. And here are the parameter dependence, and I have to divide it also with this extra term. And it's in exponent. And then for this variable defined this way, I get the modified Boussinesq equation. Even with this extra xx term, which is usually there. So I would say that this is the discrete version of the modified Boussinesq equation. Okay, so let's have some conclusions here. This is more or less something about the classification of discrete equations. Of course, we have some good results already, and partial results in the three-component form. And if you are working with the bilinear hierarchies, then there's always the Mivas transform that gives you the discrete form. This is a very powerful approach. Then there is this direct linearization approach of the Dutch school. And there are several isolated results now. So either you can say that the discrete systems, it's very rich, or you can say it's a mess. It depends on you. So now this is more philosophical question. What should we require of a discrete version of a continuous equation? At least we require that its continuous limit is the equation we are talking about. But perhaps we should require a little bit more. But what? I don't know. So I have only considered here the Boussinesq equation because it's a little bit more complicated because it's second order in time. So it gives a little bit more things to worry about and also more results. So here are some of the references. And I have prepared for you this electronic reprint. The first 50 persons who go there will get a free download. It's like a reprint, really. Unless your library has this subscription to this. Okay, thank you.
Any questions? You have sort of two approaches to discretizing. So in the first case is purely bilinear, and the second case is based on consistency. So in the second case, do you have bilinear forms of those systems? And in the first case, do you have the gauge invariant combinations which would correspond to the field variable of the Boussinesq?
In a continuous case, I can always non-linearize a bilinear equation.
Yes.
But in a discrete case, it's a little bit more complicated because a derivative is not a unique thing.
Yeah, so for example, there was one bilinear equation which has the cube roots of unity, so you would want to have a combination of the tau functions which was real, I guess, if you want.
Yes, this is a problem, of course.
Yeah. So that's still open.
Yes. While another thing to note is that in a bilinear world, if you have one component in an elementary square, it's trivial equation. There's no such thing. So bilinear equation is a little bit somehow bigger. So it's not so easy. In the continuous case, you can always use integration and so forth to go back and forth between the bilinear and nonlinear form. But in the discrete case, it's much more complicated.
So in your continuous limit, would you be able to get the hierarchy of the continuous equation?
This has been done before.
Yes, I know. In principle, once you get the first term fixed, then you don't have any freedom. Then you can look at the next expansion in epsilon, next term, and those should give the hierarchy. But I haven't looked at that.
So in the case of modified Boussinesq equation, by similarity reduction, you can get 104 equation.
Yeah.
Can you do something similar?
No, I haven't done, but there should be somebody in the audience who has done that. No?
It's done.
I don't know. Oh, yeah, you would do that.
So Jarmo, regarding the last question and the conclusion,
Yeah.
what would be the continuous analog of the reduction of the Mivo equation?
Of what?
Of the Mivo equation. Probably doesn't exist, that reduction.
Wait a moment.
So thinking of the Mivo equation as a discrete BKP hierarchy.
Yes.
So you're applying this reduction to the BKP hierarchy to get Boussinesq equation,
Yes.
which in the continuum limit seems rather strange.
Yes, that's right. Yes. This is a peculiar situation that happens because I'm working in a BKP, and I normally I get KP, I get Boussinesq by normal reduction. Now I'm working in another class of equations, the BKP equation, and by some strange behavior, I get very close to that, but the solution is not exactly the same. There's some, it's not the plane wave factor is not the same. There's subtle differences. So I do not get exactly the same, but I get very close, and this needs more research, in fact.
Just by the way, if you want to add another equation, discrete Boussinesq equation, there's this pentagram map by Kabachnikov.
Yes, exactly. I know.
And that has a problem because it doesn't have separate continuum limits. You have to do the continuum limit simultaneously to get.
Thank you very much for this question, because Maruno-san just brought this problem to my attention, and he noticed some results, and now on the boat here I did the calculation. Now I can calculate the double continuum limit of the pentagram map in the Gleich formulation, and I do get Boussinesq equation. Gleich.
So separate limit?
No, just as before.
Ah, very good. Okay.
Okay, so let's thank Jarmo.